Hello and welcome to the part B of my last video for separations. I have a little agenda on the screen which shows what we are going to do today. In the first section of this, we are going to derive the normal equations for multilinear regression. And to do this, we will be using the geometric argument that the residual must be perpendicular to the columns of the design matrix. I know that sounds rather complicated, but we will go through it step by step and explain that. And the second part is we are going to transform the Antoine equation into linear form. And to do this, it's going to fit the parameters to water vapor pressure in our course and of course GitHub. And then we are going to compare those data points and the fitted model to a semi-log plot. And to do this, we will be using Google Colaboratory, which I've used in previous. But for now, we're going to be working on this iPad, and we will get down to the basics first. So you could be obviously wondering, well, how exactly are we going to go about this? Now, just so we are on the same page, multilinear regression is this as follows. So essentially, you would have a bunch of points scattered all over your graph, like that. Now, the multilinear regression is going to be represented by a line that best fits all of those points. It's probably not going to be a straight line like that, so I don't want that. It's probably going to follow a curve or something like that. We will obviously see this better when we graph it. And to follow along with this, we're going to be using matrix math. And to do this, you'll have a matrix as follows: x1, x2, let's make this a little bigger, x1, x2, all the way to xn, which will then be multiplied by the slope, which is always m, and our y-intercept, which is b. And this will result us with our y-coordinates, which will be y1, y2, all the way to yn, and so on and so forth. And now from these matrices that you guys can see, we get more of our generic expressions that everyone is more comfortable with, which is going to be mx plus b equals y, or we will write this as x1m plus b equals y1. And then we will follow this all the way down the line. And so if you had 7 terms, you would go to x7. If you had 30, if you had a million, you would go all the way down until that nth term. But so we have only x1 and x2. And then the final term would be n, which is just representing essentially in any amount of terms that you want to go to. And now from here, we will be able to derive our normal equations. So now we are going to be looking at solving for error in vectors. And to do this, we will draw a graph in which we would have a vector going here. And we can say that this is at 3, 1. Now, you will have, obviously, we'll draw this in purple, you would have a vector going this way. We can label this as I. And then we would have a vector over here as our error. Now, to get the smallest amount of error, we want to have it exactly perpendicular to this vector. So we would assume that this is at 3i, and we want our vector going straight up to get that exactly perpendicular. And now from here, we would use the dot product to help us solve this problem even further. Now, the reason that the dot product is so important is because when we're looking for this error and we want to minimize it, when we find the dot product is equal to 0, that means the error is going to be equal to 0. Now, you may be wondering, how do we find this dot product? Well, to find the dot product, you're going to use this equation that we get from these matrices above. So I'm going to label these things as A, C, and Y. Now the equation for this dot product is as follows. Your error, sorry, this isn't, I misspoke. This is going to be for your error equation, not the dot product. The error is going to be equal to that y value minus the product of A times C. So now the next step will be transposing our matrix. And you may be wondering, what the heck does that even mean? That means when we want to flip this, right now, as you can see, it is in a bunch of rows. Now we want it to be flipped horizontally into columns. So we're going to label this AT for transposed is equal to x1, x2, x3 to xn. And we're going to multiply this by our error. And now, like we said at the beginning, you want this to be equal to 0, so you know AT times E is going to be equal to 0. And now it is our job to find out what values in that error matrix will equal this equation to 0. So now we are on to the final step of this, and I will try to keep this on this last page. So as you can see here, we have this E equals Y minus AC and ATE equals 0. Now in common, they both obviously have that E value in which we are going to plug in. So AT times Y minus AC is equal to 0. Now distribute that out. A transpose times Y minus A transpose times A times C is equal to 0. And then the final step will be to put these on opposite sides. So ATY equals ATAC. Now, you may be wondering, what exactly does this even mean? But this is all it is saying is that when you transpose this, and B obviously is going to be equal to this Y matrix C when it is transposed also. So when you turn A on its side, you also want the Y values to turn on the side and still be equal to each other. So this equation is essentially proving that. And now we want to move into Bernoulli's equation, and from there we will go into Google Colab. I mixed up my words. I don't know why I said Bernoulli's. I meant to say Antoine equation. And so from here we're going to write that equation down, which will be log P equals A plus C over B plus T. Sorry, actually this is B over T plus C. And what it's going to help us do is solve for this matrices problem that we had earlier, in which you have our matrix C that we will label A plus this C is going to equal Y. And what we will be solving for, I will highlight, which is right there. Now the next step in this process is going to be taking this T plus C value and multiplying it out to all of the problems to get it out from the under the denominator in that B value. And what you are left with is, T plus C times log of P, the pressure, equals T plus C times A plus B. Now, we will multiply all of this out. So you get T log of P plus C log of P is equal to TA plus CA plus B. Now, what we go from here is that when you pick your desired chemical or whatever, the values CA and B are going to be given, not necessarily given, but they're not going to change. They're going to be the inputs. That's the word I'm thinking of. They're going to be the inputs, and the temperature and the pressure is what's going to be changing. So every term that you see that has a T or a P in it is going to be changing. Not changing, but they're the outputs, essentially. So this C, A, and B term, the inputs can be all grouped into one, and we are going to say that we'll use that variable. I forget what it's called, honestly. I forget what that's called. That is going to be equal to CA plus B. So let's rewrite this. T log of P, C log of P is equal to TA plus that variable, which I'm going to look up next time I pause. The variable is called alpha. I do not know why I forgot that, but so alpha. Now before we get into our matrix work, we want to get this TP log by itself, and to do that we will be left with TA minus this C log of P value plus alpha equals T log of P. And now we are able to do some work with our matrices. So let's take this equation and create a matrix for it. So we will start here, and our first thing we're going to work with is temperatures. So let's label T1, T2, T3 down to Tn. And then the next thing will be its next dependent, which would be the negative log of P all the way down to the log of P, which is 2 ... and we will put 1s next to all of this. Now, what we will be multiplying this out by will be our coefficients, which we have labeled as A, C, and alpha. And this is going to equal our final term of T log P, T log of P. So now the final step is to actually get these normal equations that we'll be using, in which we see that this alpha value here is equal to AC plus B. And what we actually want to solve for is this B value, which is equal to alpha minus AC. Now, this is our first normal equation. And our second normal equation is what we highlighted up here already, which is AT y equals ATAC. And again, that T just means it has been transposed. And we will box this off. And these are the two normal equations we had to solve for that will allow us to work better in Google Colab. As you can see, we have moved over to Colab. And the first thing we are going to do, as always, is import our libraries. So the first will be NumPy. And then the second will be the subplots. So we can go back to one of these that we've done before that we know works. So I always do this because I know this code works, so I know that there's not any little minor syntax errors in what I'm copying from. So we can copy all of this, send this over to here, and again, we don't need to integrate. We're just making a subplot here. We're not using that. So we can do this, and now we have our libraries imported that will allow us to do basic arithmetic and then also plot these subplots. So now the next step will be pulling from a file that was in our class's GitHub, what has the water vapor values. So you go into this, I already downloaded it. You can see water vapor pressure.csv, and what we're going to type in here, we're going to add, not text, we're going to add some code here. And we will start with raw TP. And then this will be pulling from that file. And to do that, that function is gen from txt. Sorry, I forgot the period. np gen from txt. And then you have to type in the actual name of the file, which will be water vapor pressure space 1. .csv, and then comma delimiter equals x. What am I thinking? Okay. And then we also have to define some of the variables here. Let's get rid of that so I can see better. And then we will also have to say T is equal to raw TP. It did it for us there, but this is not what we want to set equal to P. We're going to do that equation that we already derived, which is going to be log P is equal to NP log 10 raw TP going to be equal to, that is exactly what we want. And now we can run it and see, shift enter, np dot, let's try that. np is not defined. I'm gonna look at this and I'll be right back. So that took me a minute to figure out. It was being very weird. I realized that it was weird. I accidentally downloaded it twice. So originally I had the like one indicator here. So I got rid of that and it still wouldn't work. So I actually had to go into these files. I scrolled all the way down to this water vapor thing. I had to open it up and then I went into here. I clicked these and I had to do copy path and then I guess I needed a backslash. I'd never have known that, but now I do. So we were able to continue with this coding process. So next we're going to have to code in a couple equations based on our matrices that you can see off this equation there. So first we will type in our A value, and the code for this is a little bit funky, but it's going to be equal to np.c, do some brackets there, t, and these are just all of the variables that we talked about earlier when we were deriving. We'll have our y, our other matrix, which is equal to t times log p. Why am I not typing good? And then we will also have another line of code for our coefficient matrix, which will be A, C, and so originally I had that alpha value, but we'll just call it D because there's no alpha value on this keyboard, which will be equal to np.lin.al.solve. And we have A dot T, which is transposed at A. And then we also have A period transposed at Y. And this needs to be the same as the, what did I just do? Oh my gosh. I just deleted everything. Hold on, I gotta fix this. So that took me a while to figure out. I accidentally messed it up and I had to retype all of it, and then I ran just to share with you guys some of my errors. I forgot this underscore here, so it was giving me a bunch of errors. And then another error popped up because I originally had parentheses instead of brackets, which I never knew that made a difference, but those were some errors, and now we were able to continue coding because all of my lines are running correctly as of now. All right, and so now we're actually going to start making this give us a graph. And so we will start this by making our t-plot, which is going to be equal to np.linspace, and that will be t-min, t.min, we have t.max, and then we have our number of values, which we will set as 100. And we also want our Antoine equation, which will be equal to 10 times A minus B divided by this t-plot that we have plus C. Now let's run all and make sure that's good. Okay. And then next we have to actually make our plots, which we'll do. You know what, we can go into here, which we've done before, and we have all of these, so we can copy some of this. Obviously we'll be modifying this, but we want our subplots, so we'll delete everything up to there. So we have our make our subplots, and then this is going to be equal to x equals t, y is going to be equal to 10 log p, and then mode equals markers. Let's see if this will be nice and suggest It did not, which is fine, but this will be x equals t plot. Oh, there we go. That is exactly what we want. And then the last part will be fig dot update, and we want to update our axis here, our y specifically. And that is going to be type equals log. So now ideally, we are going to make this plot, which will show us a semi-linear log graph. The y-axis will be log, so it's able to show us an actual curved line. And then the bottom, the x-axis will be linear. And all of the points should be equal to or close to a value of error, which is 0. And as you can see, this is our graph. Like I said, on the left side, this is log, this is linear, so it is a semi-log. And you can see the linear regression line here, which fits all of these scatter points. And according to the equation that we derived earlier, all of these will have 0 points of error. So thank you for watching my video. This is the second portion complete, and I appreciate your time.